Our next session is entitled Ushering in an Era of Quantum and AI for Science. This distinguished panel is being moderated by Dr. Bob Sutor from the Futurum group. And our panelists include Dr. Krysta Svore from Microsoft, Dr. Charles Tahan from Microsoft, Dr. Rajeeb Hazra from Quantinuum, and Dr. Chris Langer from Quantinuum. Please join me in welcoming Bob, Krysta, Charlie, Raj, and Chris.
All right, well, thank you for joining us toward the end of the day here. Just a couple of preliminary remarks. First, let me repeat our title here, Ushering in an Era of Quantum and AI for Science. Quantum and AI, those words have been used together an awful lot. Is it quantum for AI? Is it AI for quantum? What is the mix? We'll be talking about all those sorts of things. You made some really exciting announcements this morning. We want to get into that. And let me just, on a personal note, I was with vendors for 4 decades. And so I decided a few months ago to try my hand at being an analyst. And so I cover quantum. And all I get to do, it seems, is write about you guys, right? So, I mean, Quantinuum, I think I've done in 6 months, 4 of them. And of course, Microsoft has to join in, right? And that's all really kind of leading up to where we are today. So what I want to start doing is really going to the announcement, because these are the numbers. Then we'll get into a little bit about what it actually means and the goals and things like this. But Krysta, give us the speeds and feeds of what you folks have done together and the momentum this demonstrates.
Yeah, well, we are thrilled at Microsoft to be working with Quantinuum on bringing forward logical qubits. And in April, earlier this year, 5 months ago, we shared that together we had brought to life 4 logical qubits, the most reliable logical qubits on record, and that these were 800 times better than their physical counterparts. So really entering the era of reliable quantum computing. And today we shared that we have now been able to achieve 12 logical qubits on the H2 system with Quantinuum. And these 12 logical qubits have been entangled. So this is the largest entangled logical state on record and has the highest fidelities. And these are 22 times better than entangling 12 physical qubits. So we're thrilled to bring forward more logical qubits and then also bring together error correction and computation, create fault-tolerant computation with logical qubits and compute, right? We actually create a graph state and we can error correct that state while we do that computation. So really bringing forward logical qubits, more logical qubits, 3 times more in 5 months with less than doubling the number of physical qubits underneath.
And let me just ask here, your definition of logical qubits, because I swear I've seen 4 or 5 of them in the last. So
yeah, definitely logical qubits. All they can come in different flavors depending on the definition. And here we're really speaking about encoding in error correction. So here we are doing error correction, and we are doing better than physical capability, right? We want to show that these are better than using the physical qubits alone.
And Raj, what is it? Why Quantinuum here? I mean, Microsoft's been around for a long time. I mean, lots of platforms. We'll talk more about Azure and what you're doing there. But what is it that Quantinuum really fundamentally brings to the table that allows this?
Well, I mean, I share Krysta's excitement about working together because in many ways, the results that you just spoke about and our teams collaborated to work on and create is validation of a core belief of ours, which is you can't just create qubits. It's all about creating useful qubits that can do computation, that can actually implement a circuit of use, of value, and do that work. And so from day one, we've been on a mission to actually not get defocused by what I call the qubit race, but to focus on building the highest quality fidelity qubits that we could find and make. And it wasn't about hundreds of qubits or thousands of qubits. Our goal is to build those qubits that innovation like the qubit virtualization work can effectively use to create these stunning results of 12 logical qubits out of 56 physical qubits, right? It would be easier in a kind of wasteful sense to say, we'll create 10,000 qubits and you could create 12. You'd still have 12 logical qubits, but that overhead would be a wasteful resource spend. And that is, so this work is validation that not only are we on the right track, but we are well ahead in terms of making that vision come true with partners like Microsoft.
Chris, 12 qubits? What does that really mean? I mean, you know, we talk about exponentials sometimes and quantums and things like this. 12 qubits isn't one better than 11, right? Can you talk a little bit more about, you know, this progression of how much better it is?
Absolutely. I mean, 12 qubits is twice as good as 11. Now, it's still classically simulable at 12 qubits, but once you get to 50, it no longer is. And once you get to 100 and 1,000, it's just literally impossible to be able to do this. In our H2 system with 56 qubits, not using logical qubits, we did perform a random circuit sampling experiment where we were very careful about showing that it was not classically simulable. One of the benefits of our machine is we do have all-to-all connectivity. And so in this random circuit sampling experiment, the all-to-all connectivity actually made it even harder to simulate. And so it was a good example of some quantum advantage. But let me come back to the all-to-all connectivity just for the moment. This ratio of 12 logical qubits extracted out of 56 really was enabled by all-to-all connectivity. Because this is what enables these really high efficient codes, and you get other advantages as well, like single shot error correction. And so when we set out to build our computers, we really wanted to focus on making the qubits useful. And for us, what that meant was getting the highest fidelity gates that we could possibly get, as well as the most connected qubits that we could actually have in our machines. And this is what enabled this great result.
So one thing I very much like about what you've announced here is you've highlighted what you did really in April, right? I mean, you've shown this progress in about 6 months or so, shall we say. Yesterday, I hosted a workshop. I used the Apollo model for the different phases of quantum computing. Krysta, you have a slightly different model. It's still three phases. I want to make sure I get this right. The foundational level, the resilience level, and the scaling to really a quantum supercomputer. What does this announcement mean along that type of roadmap and development? What's the goal?
Yeah, so definitely I like to think about the world in 3 simple levels of quantum computing, right? And so level 1 is noisy intermediate scale quantum. That's this, we call it foundational. This is where you're operating directly on the physical qubits. Level 2 is when you have, say, growing upwards to say 100 or hundreds of logical qubits, and these logical qubits are operating better than the physical qubits. At that level, you can achieve scientific quantum advantage at around 100 logical qubits when those logical qubits are good enough. And so when we say scientific quantum advantage, that means being able to achieve a solution using the quantum machine integrated with HPC and AI, for example, a solution that you couldn't otherwise achieve with classical compute alone. And then level 3 is about scale, and that's where you have thousands of logical qubits. And this is referred to either as the commercial quantum advantage stage or level, or sometimes the industrial quantum advantage. And there you're looking at solutions for chemistry problems, right? Industrial grade chemistry problems, again, at thousands of logical qubits with much better logical error rates at that level as well. And so what we've announced and shared together, bringing together the qubit virtualization system of Microsoft alongside and along with, right, the H2 system from Quantinuum, is that we have, right, logical qubits. We've entered level 2, right, this resilient era.
So, Raj, I've heard you say that we're nearing the end of the discovery period, if you will. And so it's clear we're going through phases. And at conferences like this, I do think it's very important to realize there's a lot of history to the computing industry and things. But you use the word okay, we've been in this discovery period, we've learned a lot, and now we're going into the acceleration period. What do you mean by that?
Well, truly, the last, I would say, for the industry, this is not just particular to Quantinuum, discovery has been on multiple facets. First is the foremost discovery technologically, right? From modalities to various ways of controlling qubits, questions about scale. In the discovery phase, we had more questions than we had answers. It was discovery around who to work with, whose goals were aligned, what partnerships could be created, so technical ecosystem. What I mean by we are now in acceleration phases, we have certain things that have settled, and we know that that's what the rest, the future is going to be built on. Doesn't mean everything is known today, but some of the eigenvalues, if you will, are set, right? And so for us, that is belief in the trapped ion QCCD architecture. We know how to scale it. We know now how to control larger number of qubits. We now know how to maintain those fidelities or improve them. And we know who to work with in order to bring and accelerate these stunning kind of logical qubits or entry into the resilient era. So now, it doesn't mean that discovery goes away. Discovery never goes away, but now we have enough bedrock to start building the scaffolding faster.
So we will only be talking using linear algebraic terminology from here on, just to be clear.
Sorry, I had to do
That's fine. No, I'm with you on it. That's cool. I'm a math guy, so I love it. Charlie, a little bit of your perspective on this, but first for the audience, what was your previous job? You haven't been at Microsoft that long.
2 months.
2 months.
I was previously director of the National Quantum Initiative and also chief scientist at Lab of Physical Sciences for the NSA.
So could you talk a little bit about this really from a momentum perspective? We're going to get back to use cases in a moment and mix in some other things. But as you were doing things with the government, really looking at the broad national level, you clearly had to have some sense of, are we there yet? What are the measures of success? And what does this mean to you, this type of progress?
Well, it's funny, you were talking about the history of electronics industry. We're kind of now old enough to have some history of our own in quantum. And if you want a good laugh, you can go home and Google quantum computing roadmap Los Alamos, and you'll find circa 2001 what the community thought the key milestones were for quantum computing and an associated timeline. And I say this because it's really easy to, because it's taken a little bit longer than we thought, that people, I think we're on like step 3 of that roadmap. It was very, very aggressive or optimistic. But it's easy to forget how big a milestone this is, like proving that quantum error correction works in a variety of codes, in a variety of systems, was not an obvious thing when we started. It was the key milestone that we're all working to for more than 2 decades now. So it's a big deal. Like, we should celebrate it. Like, it's like when you become a scientist and you write a paper, you do some work and then you eventually write the paper. You're so exhausted by the time you submit it that you don't care anymore. Like, that's kind of, it's dangerous to be there because we're in a really exciting place. And I think it really is a phase shift to where, okay, quantum computers are going to work. Now it's a matter of how fast can we get there to real value to people who want to use them. And I think that's the exciting place we're in. And so from that perspective, thinking nationally or internationally, we still don't know when that economic value will be completely unlocked. But we have a pretty good idea now that at least scientific value will be here very soon. And we have trajectories that look very promising. So I think it really is an exciting time that we shouldn't forget.
Can I amplify this a little bit?
Please.
Because I think this is a really critical point. And 20 years ago, I was involved in some of the earliest work on taking noise parameters that might look like what physical hardware would have and modeling for the first time what error correction would do. 20 years ago, we were doing that modeling, and it's this work here that we're talking about, right? The 4 logical qubits we stood up in April, that was the first time on record it outperformed physical baselines. And that was a dream come true for me, right? Being involved in some of those early models and then seeing error correction works. This is real. And now it's almost like 5 months later, we're almost taking for granted already that logical qubits exist, right? We're using the language all over, right? It's all about logical qubits now. We have really accelerated, I think, to Raj's point, right? That we are now in this time period of real acceleration, right? Discovery of logical qubits is done. Like now we're accelerating towards 50 and 100 and more, right? But this is a remarkable, remarkable time, right? That this theory works in practice, right? We have taken theory to practice here, and that's a big deal.
Chris, these wonderful qubits don't just live out there by themselves. Tell us about the H2 system.
Well, yeah, the H2 system is an ion trap-based quantum computer, and it's based on the quantum charge-coupled device architecture. In this architecture, 1 qubit is 1 ion, and it's not fixed in place. You can move it around. And we have dedicated zones where we perform our operations, and we just want to do operations on 1 or 2 qubits at a time. We move them to those zones. We do have also parallelism. We can do multiple operations at the same time across multiple zones. But the key steps are rearrange the qubits, and then gate them, and then repeat. And it's very easy to understand, but it gives you all-to-all connectivity, and you actually get simplified calibration to do the gates in the dedicated zones. This is how we achieve high fidelity.
Okay, so now I think we've covered pure quantum, if you will, for a little while. Let's toss in some other things, because if we look at the title, we're talking about science. Krysta, when I saw you speak earlier, I like to use the word practical quantum advantage, because there have been so many, but you use the term science or scientific quantum advantage. And that doesn't just mean science projects in the back. It means real science, and we benefit from science, obviously, in every way. Let's start combining, so the quantum, these types of progress with what AI can bring to the picture and HPC, because after all, this is computation, right? We don't have to be purely one or the other. But what sort of problems can we solve? Have you made progress on that?
Yeah, absolutely. And again, on Quantinuum's H1 system, we've shown an end-to-end workload that brings together cloud-based high-performance computing with reliable quantum computation on H1 in this case, and then also AI, right? So what we do is to solve a scientific, right, we want to solve scientific problems here. You can solve other problems too, but we believe the first advantages will come for problems in the space of science, in particular materials science, studying quantum magnets, and then also leading out towards chemistry. And so together, we have demonstrated an end-to-end workflow that really looks at a problem in catalysis, right? So you want to understand a catalyst that can help drive, for example, if you're looking at drug synthesis, drive a drug design towards a chirality, right? A handedness of that molecule that would lead to a therapeutic benefit as opposed to a harmful effect, right? So naturally, that's what you're looking for in drug design. And so we've modeled that for using HPC, quantum computing, and AI together. So we use HPC to explore the reaction network. And in fact, on the HPC side, we use Azure HPC, something called Azure Quantum Elements, which is our scientific platform, our platform for scientific discovery. And there, this is the first automated reaction network exploration in the cloud. So we've really brought that to scale by taking that capability to Azure. Then we take that exploration and also use HPC to identify the active space that is strongly correlated, and we get a list of those out. We can take, for example, we took one of those in this demonstration and then used a quantum algorithm to instantiate the quantum state there, and then we measure the logical qubits. We use the quantum algorithm on logical qubits. We measure those logical qubits and use the classical data from those measurements to train an AI model. then we can use that AI model, we can probe the AI model, right, for estimates, for example, of the ground state energy of the quantum ground state that was prepared, for example. So this is really a first end-to-end demonstration. We did also post a technical paper on the archive on this in the last 24 hours. But it's an end-to-end demonstration. Now, this problem, indeed, you can still solve classically, right? You can get the true ground state energy exactly. But what we find is it's logical qubits that help us sample the true ground state energy here. When we do it with physical qubits alone, it's not as good. And in addition, this is really a proof of concept for how you want to scale your workloads going forward, right? So this is really a demonstration of the modern application, the modern scientific application. Ultimately, we want to scale up, have more reliable quantum computation there, right? Scale up the number of logical qubits, how good those logical qubits are, and enable this for larger and larger problems going forward.
So Charlie, so turning back to you, so this is a very specific project, type of problem you've solved, a real workflow, right? I've been involved with quantum about 8 years or so, and people keep trotting out the usual use cases for chemistry and things like this. And I've wished that they would take it down a level or two. But how do you actually do this? You know, do you just plug it into a quantum computer, and there you go, and there's your answer, and away you go? In reality, any type of business, any type of computation is a series of components. So Charlie, how do you see this mix? So we have Azure Quantum Elements, which isn't just quantum anymore, right? But how do you see this broader picture of scientific computation now, the mixture of things?
Yeah, look, I mentioned before, it took us 25 years to get where we are today in quantum, at least. But what you're seeing now, and I think it's true for a lot of fields, but especially in quantum and AI, is that the pace of innovation really is happening faster and faster and faster. And this combination of extremely large compute with new models of computation, whether it's AI or quantum, combined with a lot of good data, is letting us compress a lot of learning very quickly and give domain experts, scientists, really superpowers to be much, much, much more productive than they would normally be. And that's going to just keep happening and happening for the next 5 to 10 years, at least, right? And that to me is the whole story. Like we're going to, and a good analogy is what we've seen with the new codes that have demonstrated this advantage with Quantinuum, for example, that Krysta's team has developed. Humans are creative, right? So for a long time, we've developed all these codes. We didn't have any hardware to test them on. They were this good. It projected this type of system needs, right? Millions of qubits to do anything useful. Suddenly, we actually have hardware. Humans are creative. We found much, much better ways to use them to reduce the resource requirements. If you asked me even a year ago, would we have 12 logical qubits, I would have said there's no chance of having 12 logical qubits today. Even a year ago, maybe 2 years ago, right? And if you combine that ingenuity with the ability to search over very large spaces and develop AI models specialized to both making better codes or computers or making better calculations, it's going to just keep accelerating. So I think we're going to surprise ourselves. That tool set is going to enable our creative people to be so productive that the next 10 years are going to be dramatically faster than the last 10 years. Like there's a lot of evidence of that. That's what makes me excited. Like it really is a foundational shift. It's a number of different technologies developing all at the same time together to enable that.
And I think that's important for people to see. You've been in this for a while. You see it every day. What really excites you, you say, oh, this is different. Now the game.
Yeah, there's a phase change that's happened in the last year, 2 years.
So I have one more kind of biggish topic, but just before I go to that, Raj, do people have to wait? I mean, is this a nice little, you guys all work by yourself and things like this? Should you be waiting to try to do this real true integration, really, of the different types of computing, AI, the classical HPC, and quantum, of course? Is this something people should start working with today?
Sure. Before I answer the question, I was patiently listening to Krysta and Charlie. This is the kind of stuff that keeps us going, right? I fundamentally look at this as a whole new way to do discovery. It's like creating a new version of digital lab, or a digital lab where you have a digital persona called AI, you have new sets of tools that digital persona can use, called a quantum computer, generating data that could only be approximated and modeled before. So this ushers in almost like, you could say, industrial revolution. This is a discovery revolution. And in many ways, AI is the best thing that could have happened to quantum computing, and quantum computing could have been the best thing that happened to AI. And fortunately, they happened kind of together, right? So the short answer to your question is no. Discovery process is not about big bangs. You get started, you learn, you modify your discovery, you strengthen your tools, and you do bigger and bigger problems over time. So the time to start is now. If we had been 5 years behind, if this was 2019, I would have said, maybe the quantum computers aren't just quite there yet. Maybe the large language models or quantitative models aren't there yet. But no, they're here.
Okay.
And only our use is going to make them better. They don't sit on shelves and get better, right? So if we have to make progress, we got to use them now. And the good thing is there's plenty of value to derive even today.
So we just have a few more minutes. I'm Krysta and Raj, I'm going to let you highlight this. So one question each, no more than 2 minutes. Krysta, this term collective genius that you've used, how do you apply that term? What do you mean by it in this context?
Well, really, collective genius, when I've used that term in the past, it really means to me bringing in minds around the world, around the globe. We think about empowering people, empowering scientists, empowering students, empowering our children, young people everywhere. That collective genius is about really ensuring that everyone has, not only a role to play here, but has the ability to enter, right? That has the ability to use these capabilities to perform their own discovery, right? So I think to get, when we think about reaching scientific quantum advantage, it's not just what we on this stage are going to be doing, right? It's not just the engineering and building of the machine and the tools and the hybrid workflow, right? It's also those that use it. And it requires a collective global genius, diverse genius coming together. The applications that we've thought of are probably not the applications that ultimately are going to be the ones that are consuming the most of this hybrid app time, right? It's going to be something new and different. So it really does require the collective genius of our entire globe.
So Raj, final. So in the AI world, a lot of people refer to responsible AI. And that means something very specific in terms of bias and so forth, different privacy and so forth. What does it mean to use this combination of technologies responsibly, right? Is this all to create, if I may, things that explode, right? Chemistry? What does this mean? Dual use, this term comes up. What's Quantinuum's approach to this as you're making these solid innovations?
Great question. Our fundamental belief, our fundamental passion is that our large societal scale challenges, whether it's in food security, whether it's health and wellness, whether it's in making life at play, out at work, better, that quantum computing and AI, these digital tools, can have a tremendous benefit. I mean, I think about the days, people talk about personalized medicine, but think about self-healing systems. Mm-hmm. The computational biology work that we could do to analyze and self-heal systems, longevity, right? I mean, these are the kinds of things for the first time we dare to dream to do for humanity using these tools. Mm-hmm. Sure, there can be misuse of tools. That's not new to quantum and AI. That happened with HPC as well, and all of the digital tools. But the benefits, when used responsibly, so dramatically outweigh the possibilities of the misuse portion, right? That we have chosen as a company to focus on what good we collectively, through the genius of our partners and everybody around the globe, can bring.
Well, thank you all. First of all, because of the result, right? Which is tremendous, but also I just love seeing partnerships in this, right? It's going to take an awful lot of people to get us over the finish line, and then we're just going to keep going. So very strong partnerships of this are essential at the large level and the very small. So it's been a great day for you, great news, and thanks for joining me this afternoon. So thank you very much.
Thanks.